Hello, and welcome to this special webinar on the future of drought in Texas. What do researchers and stakeholders need to know? This webinar is being recorded, and the video will be available on the NIDIS YouTube channel. My name is Joel Lisenby. I am the Regional Drought Information Coordinator for the Intermountain West and Southern Plains regions at the National Integrated Drought Information System, or NIDIS. For those of you who may be unfamiliar with NIDIS, we were first authorized by Congress back in 2006 and reauthorized in 2014 and 2018. While NIDIS sits under the National Oceanic and Atmospheric Administration, we have an interagency mandate to develop and provide a national drought early warning information system, which looks a lot like a network that connects folks who have drought information with those who need it. Our goal is to enable the nation to move from a reactive to a more proactive approach to managing drought risk and impacts. And in doing so, NIDIS is authorized to engage in partnerships with federal, state, tribal, and local partners, as well as the private sector, academic institutions, and citizen scientists. You can find out more about NIDIS. You can get more information about us by visiting our website, drought.gov. The format of today's webinar will be a presentation by Dr. John Nielsen-Gammon, and then there will be time for questions after each section of John's talk. He'll pause a little bit and I'll be able to field some questions. And then if there's time, we'll also open up for questions at the end. Now, with a group this large, we found that questions go smoother if you'll please just type them into the question box. And then I'll sort the questions and share them with John as we go. So feel free to enter questions into the question box as we go along, as they come into your head. By way of introductions, John Nielsen-Gammon is a Regents Professor of Atmospheric Sciences at Texas A&M University. He's also the Texas State Climatologist and has held that position for the past 20 years. His research includes extreme rainfall, drought monitoring, climate data quality, and computer modeling. John is the lead author of a paper titled Unprecedented Drought Challenges for Texas Water Resources in a Challenging Climate. What do researchers and stakeholders need to know? Which will be the topic of his presentation today. So now I will hand the remainder of the presentation over to John, and he will be able to talk to us about what the future of drought in Texas looks like. So John, I've just made you the presenter, so you should be able to take it away from here.
Okay, it hasn't registered over here yet, but still waiting for that. Here we go. Okay, so yeah, I'm going to be talking about the future of drought in Texas, although it's sort of a bit of a regional sort of scale presentation, although we'll start off with what regions we had involved with drought analyses and recent papers, and then talk about a focus on Texas. And the way this talk's going to be organized, I'll cover some past research on what we know about climate and climate change and how it's going to be affecting water. Then I'm going to talk about how those effects of, say, drought in general apply to surface water supply and groundwater supplies, and some of the tools that have been developed to deal with that specifically. And then in the last part of the talk, we'll focus on 4 prototypical water stakeholders: agricultural interests, major surface water suppliers, a small groundwater management district, and a regional water planning district, and talk about how what sort of information they need, and how to some extent there's a mismatch between what they need and what is typically available. And then we'll close with a example of a water supplier, a major water supplier that was able to do a deep dive into the climate information and extract the sort of information they needed. So the paper itself involves a long list of authors and contributors. The this grew out of a coordinated coupled natural human systems research project that was funded by the National Science Foundation and is being led by Principal Investigator Jay Banner of the University of Texas. And he's also received funding for this project from the Cynthia and George Mitchell Foundation. And partly as an outgrowth of this, that became the first 2050 Bridging Barriers initiative for the University of Texas at Austin. So that's also provided support for this. And the whole research program, at least the NSF and Mitchell Foundation part of it, involves looking at the impacts of climate change on central Texas, the chain of major cities from Dallas-Fort Worth to San Antonio and even the lower valley, and how that region is moving from a less arid situation to a more arid situation as climate change is taking place. So in terms of what's happening with climate, the most straightforward things that everybody hears about is temperature and rainfall. So on the left is a graph of temperature change, annual temperature anomalies in degrees Celsius. Two of these plots are global analyses of temperature, the first two in the legend on the bottom, and it's a fairly familiar temperature trace. You've got variations from year to year, variations in the trend, but overall long-term increase. The third plot, labeled HIST plus RCP 8.5, is a combination of historical runs and climate model projections from climate models themselves, which pretty well track the global record. I mean, they won't show variations of temperature from year to year caused by things like El Nino and La Nina because they're not trying to predict that sort of thing. You do see dips due to volcanic eruptions showing up, such as Pinatubo in the early 1990s. But overall, it's a pretty good projection. Maybe they're underestimating things in recent years, overestimating temperature rise in recent years, but certainly the basic story is there. And then the red line is, or technically maroon, since I'm an Aggie, is temperatures in Texas, and these are actually decadal scale averages to reduce the year-to-year noise. Anytime you're dealing with things happening on a smaller scale, there's a lot more variation from year to year because of particular weather systems and weather patterns affecting different locations differently in different years. But even given that variation, you can see the same sort of long-term background trend, and model projections are actually consistent with the accelerated trend in recent decades in Texas. The expectation is temperature rise will be about 20 or 30% larger than the global average within the state of Texas. As you can see, it's there's variation from county to county based on particular weather stations and weather records, but there's not a whole lot of systematic variation across the state. Temperatures are going up everywhere, recently at a rate of more than ½ degree Fahrenheit per decade. The story for rainfall, we'll look at the geographical distribution first. It's not nearly as uniform. There's actually parts of the state, particularly West Texas, where rainfall over the climate data record has decreased somewhat, whereas in the eastern half of the state, rainfall has increased by at least 10% over per century in most areas. But embedded within that is a lot of variability from year to year. We've seen especially a lot of variability in the past decade or so. 2011 was the second driest calendar year, and 2015 was the wettest calendar year on record. So we have this sort of variation going on, and you can even still eyeball the long-term trend in Texas. But unlike temperatures, the rainfall projections in Texas indicate probably decrease of rainfall, although the average among climate models is only a few percent over the next several decades. So the projected climate trend is smaller than the natural variability that we've already seen. Now, our paper was partly motivated by some of the work that was done by Ben Cook and co-authors, looking at drought risk in the American Southwest and Central Plains. This paper was published in 2015, and the signature graphic from there is a combination of analysis of tree ring data showing drought variations over the past millennium in the Central Plains and the Southwest, and then climate model projections of soil moisture and Palmer Drought Severity Index going forward. And they have this ominous drop-off in conditions indicating dryness by the end of the 21st century, that is more severe than any of the multi-decade scale dry periods going back a millennium. A recent paper that came out just this year sort of is a follow-up on that, but goes into more detail about the American Southwest and refers to what's going on there as an emerging megadrought. The term megadrought seems to be the sexiest word in our abstract of our paper. There's no really established definition of megadrought. The one that tends to be used has to be multiple decades long, and at least in the context of the Southwest U.S., they're focusing on drought levels that exceed anything that happened in the 20th century. So, for example, with soil moisture over the area of their study, which is indicated by the yellow box, we've seen dry conditions and negative soil moisture anomalies, not just in their study area, but also across much of the West Coast, particularly on Mexico. And of course, Texas has seen a portion of that also. And the model simulations and trends for the historical record show that it's been getting drier than the long-term average since just before the year 2000. And we can compare that to the tree ring record over that period, which shows that here's a couple of examples of mega droughts. A couple examples of the validity of the reconstruction during mega droughts based upon how many trees are available. And the red indicates you've got really good data available for drought reconstruction. And that doesn't include Texas back in before 1000 AD, but it does include much of the desert Southwest. By the time we get into more recent droughts like the year 1700, we've got good reliable data for Texas as well. But the mega droughts in that area, the big one was in the 1200s, and also one before that, which has been tied to the major transitions in the Anasazi civilization in the Four Corners region. And then the more recent mega drought in the late 1500s is also fairly well established. The major wet periods, actually, there's 5 of them highlighted, and 2 of them are in the 20th and 21st centuries. So we've effectively in the Southwest gotten used to wet conditions. Diagnosing their projection of increased aridity in the 21st century, they looked at simulations that just involved changes in precipitation, and simulation just involved changes in temperature and humidity, and then the combination. And for rainfall averaged over that area, there's a projection of an actual increase, mainly in the northern portion of it. The southern part is like Texas, with very little change or maybe a slight decrease. So obviously, decreased rainfall is not driving the aridity. It's got to be something else, and temperature and humidity are the only other direct factor. And this shows that the simulations of soil moisture are being driven downward by the decline of the increase of temperature and the decline of relative humidity. And that's mainly focused up in the Great Basin region and the northern Rocky Mountains. If you break things down in terms of contribution to the drought, based on the climate models, we have a 47% contribution based on the fact that the actual value is quite a bit lower than what the climate models are projecting should be expected. That's based on the fact that you've got natural variability that causes big swings. So right now the dry conditions are partly caused by natural variability, but we've got this systematic signal of drying going on, which is 47% of the total. So we have an attribution of half of this being man-made. And of that, more than the man-made signal is caused by temperature and humidity changes, and that's been alleviated somewhat by man's contribution to precipitation changes. So if precipitation wasn't going up in that region, the drought conditions would be even more severe based on this analysis. So what about Texas? Well, in this analysis, it did include a little bit of Texas, but it's hard to even say that what's going to happen in El Paso is well represented by the average over this region. And certainly we can't say what about the rest of Texas. The study from 2015 is a little bit better, but even at that, clearly conditions in South Texas aren't represented directly in either study, and it's kind of tough when Texas is lumped together with Minnesota or California. Certainly, Texas really does not like being lumped with California for a variety of reasons. So we were pleased to have Ben Cook join our study. He's a co-author, and do the same sort of analysis that was done for the high plains in the Southwest for the state of Texas in particular. He did 2 boxes, one for West Texas and one for East Texas. We didn't include South Texas because the Drought Atlas doesn't really have reliable data for South Texas. There's just not enough tree ring reconstructions in that area that have made it into the North American Drought Atlas. And this is the Palmer Drought Severity Index for the past millennium from the tree rings. And I've sort of eyeballed and highlighted the megadroughts in West Texas and East Texas. In East Texas, the 12th and 13th century megadroughts show up. The one I highlighted in late 15th century, 16th century in the Southwest shows up in West Texas as well. And in West Texas also a megadrought that coincided with the Civil War. You can also see the drought of the 1950s showing up in both of these reconstructions, which is a good sign. You can also see the relatively wet period toward the end of the 20th century, and then a little bit of dryness starting around the year 1996. By the way, a word on the scale here. We're looking at the Palmer Drought Severity Index, which is a common measure of drought severity. It's based on temperatures and precipitation. It does real well incorporating temperatures on an interannual basis, but there's been a lot of research showing that it's probably not so good looking at changes in soil moisture. But on a multi-decade scale, when there's temperature changes going on that are not directly related to precipitation changes. And I won't go into the details of that, but that's why I like to look more closely at the soil moisture projections going forward, because those are some things that are directly relevant to drought, directly being simulated by the models. But we don't have good soil moisture observations, and so we rely on the Palmer Drought Severity Index for the tree ring reconstructions. So we gotta really look at both of these in their own context, because they both have areas where they're the best tool available. But all of those measures, Palmer Drought Severity Index, soil moisture averaged over the top 30 centimeters, so about the first foot of soil, and soil moisture averaged over the top 2 meters, so deep soil moisture. All three of those show a decline. To be able to plot these on the same scale, Ben converted the soil moisture to basically the same scale as the Palmer Drought Severity Index. So in the Palmer Drought Severity Index, a -2 is the threshold for drought. It occurs fairly rarely from year to year. I mean, you know when you've got drought, so that's -2. The reason you don't actually see a lot of -2 or -3 or -4 in this plot is that this is the average from ensembles of climate models. So the year-to-year variability is suppressed here. So this is looking at basically average model conditions and the uncertainty range from the different climate models. Bottom line here is all of these different measures show a decrease, and they get into territory where average conditions by the year 2100 are comparable to your typical drought in what we would have considered to be a normal year in the historical record. I should have mentioned one other thing here. This is using a climate projection scenario, which is at the high end of the range of possible carbon dioxide concentrations. So we don't know if the models are correct. Reality may be, the models may be underestimating drought or overestimating drought. But in any case, the likelihood of carbon dioxide concentration going forward is a lower amount than what is in this scenario. So probably not as severe a drop-off as what this plot indicates for West Texas. And East Texas, basically the same sort of story. Again, a drop-off in all three signals. The same caveats apply that this is a model or a bunch of models, and it's also a high-end scenario. So how interchangeable are these metrics? I commented on Palmer Drought Index and soil moisture. This plot is showing how closely those are correlated within individual climate model simulations in the two regions we looked at. And most of them have fairly high correlation, which says you can sort of use them interchangeably. Some models do different things with them, but they're pretty close on the whole. In terms of how big a change each model is predicting in each of the indicators, this is a very busy plot. We'll just look at one example. Let's do soil moisture average over 2 meters for West Texas. So the teal colors are what the models simulate for the typical range of values during the 20th century. And at first glance, the performance is very good. They're all centered near zero, but in reality, that's because all of these have been calibrated to the historical record. So they've got to agree with the historical record by construction. What's more relevant is the change going forward to the end of the 21st century in the climate model projections. And what we see is some models have a ridiculously large drop-off, which is a little weird, especially since this model is showing very little change in soil moisture at the top layer. So I think that's probably something to be discounted. Other models do show consistent variations between the top soil moisture and the deeper soil moisture, with big drop-offs that take us well outside the range of natural variability of deep soil moisture. Caveat with that, again, this is calibrated to agree with the Palmer Drought Scale, which is interannual variability based. So in those models, that part of the story may be that they don't typically have much variation from year to year in deep soil moisture. But in many of them, we see substantial drop-offs in shallow soil moisture also. So I think they are showing substantial drying. And you can find a couple models, if you want to be optimistic, that say things will actually get wetter on the whole, that increases of rainfall will overwhelm the increases of temperature and actually lead to greater soil moisture. But those are definitely in the minority. This slide sort of combines the information from all of those charts. It's showing the average model simulations, which again have to be near zero based on the calibration of the models, and then the projected decline in West Texas and the timing of it, and then the range of model simulations. This is not the full range, this is what we call the interquartile range, which, sorry for that name, half of the models lie within this bar, half of it lie out of it, a quarter of them are above it, a quarter of them are below. So most models are predicting drying. Most models are predicting less drying in a relative sense for the topsoil moisture than for the deep soil moisture. For East Texas, a similar story, except we can be a little more optimistic. Fully a quarter of the models say that topsoil moisture will be wetter. And there's certainly a big range in model projections for deep soil moisture. And lastly, looking at in terms of probability distribution, the probability distribution here is the full range of interannual variations. So the North American Drought Atlas and the historical range of simulations have to basically agree, and they do. We get centered around zero, and the tail occurs fairly rarely. Then the pink is the interannual variability over the latter part of the 21st century. So you can see the shift toward drier conditions in all three metrics. Soil moisture gets broader, partly because of the uncertainty in the models and partly because the systematic change is much larger than the natural variability. But in all three cases, basically, based on it, compared to our historical experience, not very many years with above normal soil moisture and a lot more years with much drier soil moisture. Okay, before I move on and talk about what's driving that, I want to make one more discussion of terminology. So I've talked about megadroughts. Megadroughts are droughts that last for more than a couple of decades and are fairly severe. Now, certainly what these models are projecting going forward, at least most of them, is for drier conditions than in these past megadroughts in some cases. And the paper I mentioned talked about what's going on right now as a megadrought in the Southwest U.S. But you can't really have a permanent megadrought because droughts are abnormal periods of time. What these models are actually projecting for Texas going forward is what we call aridification. That's a good spelling bee word. It means conditions systematically becoming more arid over time. So it's not like we're going to get more droughts in a climatological sense. It's more like average conditions are becoming consistent with a drier climate. And the way I like to think about it, although this more applies to changes in rainfall than drought driven by changes in temperature, is that it's like conditions in Austin are going to become, say, more like conditions in San Angelo. Conditions in San Angelo are going to become more like conditions in Midland. Conditions in Houston become more like conditions in San Antonio. So it's not like Midland gets more droughts than Houston does, but conditions are just systematically drier overall. So that's what we're talking about. Okay, so what's driving all of this? Well, on the drying side, we have potential decreases in precipitation. As I mentioned, most models predict a decrease. We've got predicted changes in temperature, which are all on the warming side. If we get changes in rainfall extremes month to month, which are projected to occur, then that means you tend to have more droughts. Also, the model projections include a change in the seasonality. Models say basically if it's going to give less rainfall, most likely that's going to happen during the summer, which is exactly when we prefer to have plenty of rain, because that's when they have evaporation being strongest and things dry out more. Changes in biomass. Overall, we actually have we've had an increase of rainfall. We have an increase of carbon dioxide, which encourages plant growth. It makes plants more resilient. So the landscape is greener than it used to be, and that's drawing moisture out of the soil more readily because for the increased leaf area and so forth. Now, things that might mitigate it against that, if we have more precipitation, well, that'll affect things. For that matter, the carbon dioxide improvement in water use efficiency by plants means that they can get by with a similar amount of rainfall if temperatures don't change. So that at least is a factor that helps. And also, although this is not an optimistic scenario, if we do have a drier landscape, that does mean in the long term, perhaps less biomass, fewer trees, and that would decrease the rate at which soil moisture is drawn out of the soil. On the mixed effects side, which is depends on what you call drought, and I'll go into that a little bit later. Changes in extremes are going to affect things depending on how you define drought, and changes in soil moisture will affect things again depending on how you define drought. And those both go into the basically runoff versus absorption of moisture trade-off, which makes surface water and groundwater impacts different. I'll talk about those next, so I'm going to be moving on to the implications for water suppliers. But this is a good point to pause for questions about the climate change projections, if you have any.
Yeah, thanks, John. There were quite a few questions that came through, so I'm going to go through them, and if you could try to answer them as concisely as possible, that will let us get to as many questions as we can. So the first one is back early on in the talk, you showed some rainfall trends, and Rebecca asks, are the precipitation changes skewed by Hurricane Harvey?
All right. So Hurricane Harvey was in this year. So that did not have a big effect. Most of the heavy rain we get, of course, you're more likely to get flooding when you're having a heavy rain year. So that does affect things. If you look back on when we had the major flooding in 2015, for example, so that certainly helped get this up to as high as it was. But 2016 and 2018 were not major flood years, and neither was 2019, for example. So certainly you can find major floods back here. You can also find major floods in 1899 and 1921. So no, those events don't really affect our long-term trends much. Okay. By the way, if you just analyze the long-term trend ending in 2014 compared to these last 5 wet years, you get a trend that's about 3% lower. So instead of a 10% trend, you get a 7% trend. So those wet years did have a little influence.
Great, thanks, John. The next one comes from Tony. How well does the PDSI capture drought severity change in already arid regions?
Okay, yeah, the PDSI was designed in the Great Plains, and it works fairly well in arid regions. But this is a good opportunity to mention that in arid regions such as the desert Southwest, you probably don't care as much about local drought as you do about water supply drought. So much of what's going on in even West Texas and New Mexico is driven by the water supply surfaces from snowmelt, and the PDSI doesn't really capture changes of evaporation from snow, for example, and it doesn't reflect the fact that the water supply in El Paso may depend upon the snow in Colorado. So both of those are shortcomings of the PDSI.
Thanks for explaining that. One last question, also from Tony. What are some extreme historic examples that resemble the average future year, i.e., what is the new normal?
Well, yeah, we don't have a current mega drought to point to. Fortunately, it hasn't been as dry in most of Texas as it has been in the Southwest. One thing I did during our 2011 drought is I looked at where it was, and 2011, of course, would be more severe even than the projections of average conditions going forward, but average conditions going forward being drier makes something like 2011 more likely to happen. And in 2011, the amount of rain they had in Austin was similar to the average amount of rain in Amarillo. So there's a perspective. Another perspective, I looked at what the combination of temperature and humidity and rainfall in Austin was during 2011 compared to that, where on the earth you would have that combination of temperature and humidity in an average year. And the best match I could find turned out to be central Pakistan.
Oh, wow. Okay, so that's maybe not the new normal, but certainly gives you a perspective. We might wrap up the questions for that section there. A reminder to the audience, if you have more questions, especially about the next section, go ahead and type them into the question box. I'll pass back to you, John, and just so that you're aware, we have just under 25 minutes left.
Okay, thank you. Yeah, so for surface water supply, and well, frankly, for any projections, you have to be worried about whether to believe the projections or on the one hand, and how much reality should be expected to deviate from projections on the other hand, even if the projections are correct. Because there's also nature going on, for example. So our sources of uncertainty typically are, well, what's actually going to happen to the atmospheric concentration of carbon dioxide, greenhouse gases, aerosols, and so forth? How sensitive is the climate system to that sort of thing, which we call climate sensitivity? And there's been a lot of notice in the past year that some of the newest climate models seem to be too sensitive. We're trying to figure out whether that's the case or whether we've been underestimating sensitivity. It seems like they actually are too sensitive. But even the baseline less sensitive models still are showing climate change trends consistent with what I showed from the earlier models. How do we figure out what's going to happen locally, where you care about, what's going to happen in a particular place or a particular drainage basin, which is influenced by factors that maybe climate models can't simulate in great detail? You've got to somehow translate that into the water amounts in whatever water circumstance you care about. And then you have to say, well, how relevant is that to natural variability? So you can do that sort of thing. Of course, doing it involves uncertainties as well. A couple of tools that exist right now, for example, are hydrologic models that have been calibrated for major rivers in Texas that can ingest climate model projection data, and also at least a prototype model of a reservoir system that includes the hydrology and inflows that takes into account the operating rules for the reservoir. An example of that is this figure from a paper by Huilin-Galp, one of our co-authors, that basically compares model simulated droughts going forward for the amount of storage in reservoirs supplying Dallas-Fort Worth area. And the green lines are historical drought, the 1950s drought, with different projections of water demand for different years. Then the red is the early 21st century droughts in the model, and then the blue is the late 21st century droughts, which give a perspective now of the magnitude of climate change impacts, which is as large as magnitude of projected water demand scenario impacts, which is saying we need to worry both about using population growth as a important factor in long-term projections, and we need to worry about climate change as a factor as well. And Also relevant to that, of course, so the demand side, as I mentioned, and also flood resilience, because if you've got a reservoir supplying things, that reservoir may be partly being used for flood mitigation, and so that may mean that you actually start off with less storage than you would in the present day, if, as is also being projected, extreme precipitation increases in the future. Um, for groundwater supply, it's a little more complicated. It's a lot more of a diverse problem because we have diverse aquifers in the state of Texas. For fast recharge aquifers, such as say the Edwards Aquifer, which is a karst aquifer, the amount of water going into the aquifer really has a strong impact on the levels of the aquifer over time. And so the impacts of climate change are going to be felt by whether the recharge of the aquifer is going to be affected. Whereas for slow recharge aquifers, and the prototypical example of that in Texas would be the Ogallala Aquifer, the demand and withdrawals of water from the aquifer are going to be, of course, driving future levels, and those are affected by climate also. Because, for example, if you have a dry, hot year, you're going to need more water for irrigation, and most of the use of water from groundwater in Texas is for agriculture. So even if you're worrying about an aquifer that isn't recharging, you still have to worry about climate change when you're dealing with it. And most aquifers lie somewhere within that spectrum where you might have to worry about both issues. So let me talk about what this means then for stakeholders. Our first prototypical example is an agricultural producer. They're mostly worrying about things happening from season to season. And so the climate information that's most important for them is seasonal forecasts, but they also want to know how vulnerable they are to extremes. And we can't really forecast that on a seasonal basis. So the climate-driven trends of those sorts of things are relevant. And it can be useful to frame that in terms of recent history, just like I've talked about future aridification in the context of what happened during megadroughts. We might talk about the odds of having a drought next year comparable to the drought of 2011, because since each producer is dealing with a different set of circumstances, has different risk profiles and different vulnerabilities, telling them this drought is like that drought is perhaps most useful, because they can then translate that drought into that sort of actions that would be necessary in their particular circumstance. Next example, large surface water suppliers. For the most part, they are required to provide water during a drought similar to the drought of record. And so it's useful for them to know whether that's really a good benchmark, or how likely it is for their circumstance that droughts worse than the drought of record might occur in the future. Now, using the drought of record as a benchmark has a particular advantage in that we have observations of it and we can calibrate models to it, and it's a specific number. So it would be very useful for surface water suppliers to have a good way and an established, accepted way to incorporate future uncertainties into their water planning, rather than meeting a particular single benchmark, because unfortunately that benchmark is a moving target, because climate change is making that benchmark more and more likely. And it would be nice to, rather than just have these research grade models that have now been calibrated to take climate change information, to actually have the regulatory models that are commonly used by water suppliers be able to run the scenarios with climate change information embedded in them. Groundwater management districts, we're taking a small one here because they don't have typically the resources There may not be multiple engineers on staff that can go do a technical deep dive into the climate change information, for example. And it really requires a lot of effort, and you can't really do it from downscale climate models to say, how is demand going to be affected by climate change? You actually got to couple your climate model, the downscale information, to an agriculture model for the crop profiles in use in your area to be able to get at that sort of information. The last prototype we looked at were regional water planning groups. And now you're dealing with, with the groundwater management districts, you're dealing with needing to worry about how climate change is going to affect agricultural use. Well, now you've got on a large scale a whole lot of interactions to worry about. Like, okay, how is climate change going to be affecting energy demand, which is then going to affect the need for cooling water? And there's a whole set of cascading impacts that, when you're taking a holistic view of regional water issues, are sort of triggered by climate change. And again, they need tools for being able to develop a climate resilient portfolio of water supply. So they're not necessarily worrying about, okay, what's going to happen to this particular supply, which is surface water, what's going to happen to this particular supply, which is groundwater. They're worrying about having a nice resilient portfolio across a variety of supply mechanisms. And what does a resilient supply look like in the future compared to what's it look like now? And they've got, in addition to the diversity of supplies, diversity of stakeholders. And in fact, a thread running through all of this is that while you can certainly develop a way to take and incorporate climate change, you actually have to convince all of your customers and stakeholders that what you've done is reliable. And having a systematic, established way of doing that is sort of essential for being able to fight that battle and actually have the stakeholders trust what you're doing. So Austin Water has done this sort of thing with their 100-year integrated water resources plan, which is called Water Forward. And the way they tackled climate change is they brought in climate scientists, Catherine Hayhoe, to translate the global projections of temperature and precipitation down to specific stream gauge locations and observation locations. And they had hydrologic engineer Richard Hoppower calibrate that against the historical variations of stream flow based on the statistical range of temperature and precipitation. And they used those combinations of inputs to develop tools to look at future scenarios based on the drought of record and something that might be 3 times worse than the drought of record given the climate model projections. And they use that input directly to the regulatory model, the WAM model. And the key to doing this appears to have been actually working with climate scientists from the get-go, which had 2 benefits. First off, it meant that the climate information that was eventually supplied was going to be directly applicable. And secondly, it meant that once that climate information arrived, the people within Water Forward and the rest of the people developing the projections understood exactly what it meant, or at least understood pretty well what it meant and what the limitations were of that, so they could use it in the proper context. So I want to just wrap up with what we see as research needs to help bridge this connection between scientists and stakeholders. First off, better long-term perspective of what natural variability is, and also how past climate change has affected the landscape in Texas, so we can actually point back to something in the past and say, yes, this is what we're moving towards. We need better tools that can be broadly used It's great that Austin Water developed a tool for this, but their tool was developed for their particular circumstance, that connect the climate model projections, downscale them, and translate them to stream flow or groundwater recharge. We need a good way to take the best of both worlds, the drought of record being a concrete target. Can we like tweak the drought of record and say, well, how much additional margin do you need to ensure the same sort of resilience to drought in the 21st century as what we've been planning for from the 20th century? And lastly, across the board, we really need transparent communication so that stakeholders know how more reliably scientists view the own information they're providing, and also so that stakeholders understand what it is that climate scientists can't tell them and why, and how they can then take advantage of what sort of information climate scientists really can tell them. And last comment, this paper is available online. It's in a journal called Earth's Future. You can get to it by Googling my name and Earth's Future. That's not the only thing I have to say about the Earth's future, but it's the only part that's actually been peer reviewed. Thank you for your attention, and be happy to answer any more questions that have come up since our first break.
Thanks, John. Just a few questions. Victor asks, were there any parts of Texas where the 2011-2012 drought now qualifies as the drought of record?
Yes, there are. That sort of analysis basically requires looking at how the 2011 drought actually impacts the level of water supply in particular locations, and it does seem to. It's been established as the drought of record for a few locations. It probably will become established as a drought of record for a few more. I think the majority of Texas is still going to be have the drought of record being the 1950s drought, because even though 2011 drought was the most severe one-year drought in Texas, the larger water supplies really suffered from the 1950s drought, which lasted so much longer.
Okay, thanks for that. There's a comment from Sigmund that I'm going to translate into a question. So the question is, why did you use the RCP 8.5 category rather than the lower RCP model runs?
Right. So the main reason for using RCP 8.5 is, well, there's two main reasons. First, at least up through CMIP 5, RCP 8.5 was the only climate projection scenario that didn't include efforts to reduce climate change, things like the Paris Accords, that sort of thing. So it was the only one that could be used as a sort of, what if we don't do anything, because we actually do have some control over our future in terms of what the climate change actually is. Now, that's not going to be the case with CMIP 6. There's going to be a couple of what are now going to be called SSPs, sorry about that, that are going to be business as usual. And the one that's SSP 7.0 is a more reflective sort of what used to be called business as usual scenario. It's not as extreme. Second reason is, if you're trying to figure out what processes are affecting impacts of climate change, you want to use the scenario that has the biggest climate change impact, because it's easier to separate out signal from noise when you're analyzing the simulations. Now, that being said, you can always scale back whatever is projected with 8.5 and say, okay, if in reality we only have 2/3 of the climate change as is what's being projected by that, which I think actually is more likely to actually happen, then you can scale back the changes by 1/3 and just have 2/3 the amount of changes. So RCP 8.5 simulations are useful across the board, not just for that particular scenario.
So essentially it gives you a worst case scenario that you can then adapt to. Is that what I'm understanding?
It's a worst case emission scenario. There's other things that could be worse. You know, it's not the worst case climate sensitivity scenario. It's not the worst case location of actual drying given global changes scenario. So it's only worst case in one dimension, but it can be viewed as a worst case scenario for that respect.
Okay. Thank you for that answer. There was a question that came through right at the very end of question time in the last session that I didn't get to from Alias, and I might include that one here while we've got a bit of time. It reads, it looks like the temperatures in Texas, way in the beginning of your presentation, it reduced in the 50s and 60s. Is there a reason for that?
Yeah, let me go back and bring that slide up. Let's see, that was probably around slide number 5. See if I can hit that target. Whoops, wrong way. Let me use a slide sorter here. Okay, so the short answer is yes, there's a reason for it. Now, fortunately, person didn't ask what that reason was, but I'll try to answer that part also, but that's a much harder question to answer. First off, you can see just on a global scale, temperatures really didn't change a whole lot between the 40s and 70s. So we would expect a flattening of temperatures in Texas to the extent that they're being driven by global temperature change. But yes, there was actually a decline from the 30s, which was a warm period. The 50s was warm because of drought. And in the 70s, we didn't have drought. So that's part of it also. It's an example of natural variability on the drought scale that we had a bit of a decline. But that's not the whole story either, because we didn't have much drought in the 1940s, and that was still warmer. We do have natural variability on a multi-decadal scale, which probably contributed somewhat. And then lastly, it's also possible that the changes in the surface landscape over Texas contributed as well, because from the 1920s to the 1970s, say, and especially after the 1950s, well, during the 20s to the 70s, there was a large increase in the amount of surface land being irrigated in Texas, and that has a cooling effect, especially in the summertime, because a lot of the sun's energy is going into evaporating water from crops rather than just baking the soil and rising temperatures. A secondary contributor may also be the expansion of surface water, because there was a lot of reservoir building since the 1950s and mainly in that period of time. So that probably also contributed to a little bit to the decline in temperatures. So all of that stuff is going on, and it's really hard to sort out those differences. Certainly natural variability had a big effect as well.
Well, that's fascinating. Thanks for explaining that. That takes us to the end of our time for questions. I think I can speak for everyone who's on this right now, John, to say thank you for sharing your experience and your research with us. That ends today's webinar. Thank you, everyone, for joining us today.
Yeah, thank you.